Welcome back to High Performance Computing. Today we have our lecture 2 on parallel programming with MPI. And MPI stands for the Message Passing Interface, so-called the de facto standard how you do parallel programming, at least in a distributed memory fashion. It will be then later down the road in our basically lecture series and complemented with the OpenMPI parallel programming, which is more for shared memory programming. So today we start a little bit better understanding why we need HPC in terms of the idea of really leveraging these large machines with parallel streams, with parallel entities, objects, applications. You can see it in many ways what this parallel programming really enables, because of course, as we learned also the last time, we do this for several different scientific and engineering applications, and all their ideas are a little bit different from each other depending on the domains. So let's review a little bit also what we had the last time then. We looked a little bit on the idea of these applications, although we wanted to look a little bit on C programming and scheduling. We had also a broader picture and also reviewed a little bit why C programming is essential today. And you see that many C and C++ programs actually are used today in HPC. And also this is true actually still for Fortran codes. Now, in this course, we don't do much Fortran at the beginning here. So we really started with a very, let's say, short intro really to C programming. But we looked into these applications where we thought that basically many of these physics applications that are a little bit shown here, like neurosciences, simulating parts of the human brain, or plasma physics, or whatever it is you basically do. Here you see an earth science application where you have actually a multi-physics code, one for the atmosphere, one for the land surface, and one for the subsurface to really understand then the groundwater modeling, for instance, precisely. And you see also already this domain idea, which will come up in then one of the next lectures, a domain decomposition here, how you basically bring elements then in a parallel fashion. When you want to simulate a large domain, you basically break down this large domain into smaller pieces. And this can be done in many ways. We see a very beautiful Cartesian way of doing it maybe, but many others doing it also in a more mesh variant. So of course, there are different ways how you can do this. And also one of our subsequent lectures will work on this. But the key message to take is really many of these applications use C still today. It's very high performant codes that you can compile there. And this was also a little bit what we started in the beginning. We had the idea of a Hello World application that we looked in, which was quite simple. The only thing it does really was giving you a Hello World out basically directly in the command line here. But we also learned then with this that this is a little bit let's say, not the way how you should do it when you have a really big job. And job or task or application usually refers to the application you want to run in HPC on this HPC machines. So the point is there that basically the login node should be, as the name suggests, rather used for logging in, for maybe here and there compiling a little bit and checking elements. When you really want to run the job, we learned then also the idea of scheduling. So we want to use a scheduler on even the smallest clusters like Uton up to the big supercomputer that you see here with jewels, where basically the scheduler knows where which program is running. You see here an example of an earth science application, and the idea of an earthquake simulation might be basically here in this part of the large machine. Then another part is running this earth science application. Another neuroscientist is running actually on a complete different part of the system, another application. Hence, we have a concurrent access to the same HPC system, a multi-user HPC environment, as you basically can understand from this now. While today it's even also more and more happening that people also use deep learning applications. Deep learning is not obvious to you. We will see that materialize when we have one of the subsequent lectures later, which leverage GPUs. So basically here you could say maybe is someone running an encoder decoder architecture in terms of deep learning. Another one is having maybe a remote sensing application in a certain, let's say, specific hyperparameter setup, and running this, maybe even with an hyperparameter optimization setup. Something that we will also learn is actually one way why you want to use HPC today. But before diving into the details of all of these applications more down the road here in all these different lectures, the important part in this particular lecture from last time was really to understand, firstly, C programming is still on vogue today, especially in HPC. There are lots of C codes and also Fortran codes. And the second message is really we have a multi-user environment, and the scheduler is actually taking care so that everybody has a dedicated set of nodes, a dedicated environment where these applications can actually run, and where you then basically can also plan your job, so to speak, when you submit it. And the submit word was exactly what we looked into when we moved essentially from the idea of just executing this hello world, for instance, here in the command line, which directly gave the output in the command line back. We moved to something which was this job scripts, with the number of nodes or number of cores, how you name this particular job, what should happen with mails in this particular job. And still the idea was leveraging the modular environment that we learned in earlier practical lectures already, and specifying the same executable. So we still compiled the C program. We still basically have the same executable as we used basically on the command line. All we do is now basically, instead of executing this ourselves, we give it to the scheduler with this job script, more or less. And then the scheduler takes care of thinking about where on Newton I can actually execute it. And we have last time, if you remember, had this different nodes of compute to 0, to 1, to 2, to 3, all these compute nodes, which were then also different from the Newton node. And by doing this, you do it in the more or less right way. So the administrators would be much more happy if you do it this way and not really occupying the login mode very much. The other element that we have seen from this is a little bit this non-interactive behavior. Right here, we had the output directly on the command line, which was, so to speak, really interactive. You see the output directly. The idea, while we call this batch subsystem, batch system, scheduler, it has many names, this particular element of software. But the batch suggests that you basically are in the batch queue, and at some point in time, you picked when the cluster has place enough in order to be scheduled and then executed. And with this means you don't want to wait in your command line for the output. You want to continue with the work, and the output instead is then written to some kind of an output file that you see here. And this is basically then what we looked into it, that the job ID is, of course, very important when you submit. You get a specific job ID, which you then also in the QStat can always track how far we are. Is the status completed? Once the status is completed, it might be that the output file is existing and we can look into. So admittedly, a very simple idea how to do it, but also it captures the essence why you basically want to do all of that, because in the end, you would be very scalable with your applications. We will learn this also with MPI now today and also in the next couple of lectures, so that the key idea of why we want to do this is essentially a motivation of a speed up. The more CPUs or the more GPUs you want to do, the time basically it needs for the application on different systems should be reduced. And this is something what we will also explore then more in lecture 3 when we talk about parallelization fundamentals. But today we want to start early with MPI so that also your assignment can be started early. And that's why let's go basically with the lecture we have today, which is actually called Parallel Programming with MPI. The outline is basically starting then with the MPI concepts. We would say that initially we would clarify some terminologies as usual. Again, I would like reflect always to some application examples so that you know why we do all this. And of course, thinking a little bit about the concept that we had also in the last couple of lectures, especially in lecture 1 about shared memory versus distributed memory. So here we talk about distributed memory, message passing between these different memory concepts, and why basically the MPI standard is also good for portability. Then there are different MPI implementations. There will be different ways how you can use MPI with point-to-point messages or MPI collectives. And then we have to understand a little bit how we identify essentially each MPI rank and then how that can be used with communicators. Although I should say in lecture 4, we will review the communicators and we'll have much more, let's say, elaborate versions of them when we talk about the Cartesian communicator, for instance, in lecture 4. But here in this lecture, we start very simple, the basic concepts of MPI, and then also some, let's say, parallel programming basics. So how we would basically go and think now more and more in parallel. What are the stepwise elements we have to do for a parallel application? And for this, that means we have to understand a bit about the parallel program and the key building blocks, which are actually derived from the serial idea that we had in the last time. So still C compiling. If you remember, we had MPI CC used. So obviously this is also very much reused again. But here we want to introduce, and of course, the libraries of MPI in order then to also, enabling these parallel executions with a simple application example here today, which is called ping pong. The name suggests we do probably first a ping and then a pong back, as you probably know it from the simple application example, but it's a very nice and simple application to understand now parallel computing. Then you basically have, of course, a little bit more advanced application example with P and serial and then parallel, and understanding hopefully a little bit already parts of the collectives, although that comes more and more, particularly also when I demonstrate all of this in practical lecture 2.1 next week. When you have basically completed this lecture, the really complex aspects of parallel programming is something where we emphasize on. It's really an emphasis on parallel here. So programming and doing large-scale software engineering design is something which Matthias Bog and Helmut Neukirchen, Ebba, many others teach in the university. We want to focus really on the idea of parallel programming, in the idea of also scaling up to applications which could cover a whole supercomputer. So in this sense, you need to abstract a bit differently from the HPC system architecture. You have basically parallel computing there on different levels, as I said, with distributed memory and shared memory, for example. And here we really focus first on the distributed memory, and then later we will review what means can bring when we do shared memory programming. And with these ideas that we basically convey here already with several of the collective operations, why that is useful, and the idea of parallel processors doing this really in parallel for some application domain, you also get the foundations right to really start with the scientific domain applications if you want to make it scalable. So a very, very interesting lecture that is directly related also more or less practically to your first assignment. So please, I want to have your attention here. It's very important that you understand MPI when you move out of this course. Now, reviewing a little bit the terminologies. This is something MPI et al. And the parallel processing is, of course, something which has quite a long history and could be taught in a whole course, which is just MPI and maybe a little bit of old routines. But here we really, of course, go to the idea of this message passing, where you have different concepts in serial programming, where you talk about variables and subroutines, which is clear as object orientation. You have different languages that you're there in Python, Java, and so on, and implementations then that you program. In the message passing, MPI is really more or less the way to go in HPC. There's not many libraries that are basically up to MPI. As I said, in shared memory, we would add OpenMP, but OpenMP is then not really message passing. It's really accessing the memory back and forth. There are lots of concepts in this parallel programming. Basically there we talk about send and receive, simple message exchanges, but then collectives, groups of processors that do a certain element. And then the implementations, you see that, of course, there are many implementations of the MPI standard available. We already used the last time with Modular the OpenMPI standard, which is also a very broad standard, but there are many of them available on the HPC machines worldwide. And the application example then that leverages this parallel computing could be very different ways. So one example we have here is basically this propagation perhaps on a wave over this particular part of the coast. And this would give us a time. And obviously you see here the kind of surfer that we maybe also want to model that is on the beach, the wave height that we have to propagate. And by this, you already start by crunching down this big coastal domain into smaller pieces. And this is what we will look into basically in lecture 3 and 4 also. Lecture 4 also shows you that MPI is actually supporting this with a Cartesian communicator quite well, so that you can basically move the waves over a particular part of the ocean. Apparently, of course, you want to compute their physical methods. So how high is the wave, which follows, of course, again, the law of physics when you have the surrounding height of the waves and other parts like momentum and so forth. So this is a perfect example how you would break this big problem down in smaller pieces. But in order to calculate then one piece here in this domain, this one brick, the wave height, you need perhaps information on the others surrounding you. And this is where this message passing starts. You need neighborhood information, for instance, something which we will elaborate later on as well. So these are applications that can leverage this. And in this sense, you could basically do this, of course, totally just with one processor. But of course, this would take a long time. You have to basically do one processor, one after another, would tackle one of these bricks, and then over the time of moving through all these bricks could then compute the whole problem. In order to speed up this, and speed up is a very important part, and you want to speed up it in a so-called cooperative way, you all basically have the bricks here put into smaller pieces, and then basically can parallelize this so that the computing of this wave is much more faster, basically. And this is what you have to understand, that we want to solve this overall problem of the wave propagation, for example, in a much more cooperative way. And this is parallel processing. And to try it basically to the best performance as possible, maybe crunching domain smaller and smaller, or basically making it bigger. It's not always said that the smaller and smaller you go, it's better. Definitively, you have the amount of processors to be used there as well. So it's not that easy to simply say, always make it smaller in this kind of bricks. And then, of course, you come to more detail, to more granularity. You also need, of course, then the capacity of these doing this, which, of course, then also now brings us to this high performance computing elements. You really need a lot of processors that enable then us the parallel processes to be computed. One of a good example, because in lecture 3, we will talk much more about how you then parallelize this completely in the domain decomposition. Another example is here this glacier calving that you see a little bit in the video, where you have basically also here different, let's say, physical elements, which basically generate a mesh first, and then you do a parallel run on this mesh, how you would basically have this ice with a so-called Elma solver that you use for this. And then you basically have another part here in HIDEM, another physical code that then would in parallel run, for instance, on 560 cores here in order to compute then the whole calving and aspect. And this is done, of course, in a loop. And you will see that many of these physics applications, like here, when you think about how to compute really glacier calving, is always done in a loop. The same when you have the wave, you would say one time step is one loop. Next wave computed in the height, basically when it moves, let's say, over this tile here, then we will have another loop for the next time step and the next time step. So basically we talk about an iterative approach to this, where the physics are computed at each time step, and of course also taking into account what happens there, basically around, especially if you think about the neighbors. So nearest neighbor communication will be also an important part, which we will talk later. Coming back to the HPC applications, as I said before, when you now think about, for instance, the domains, you have this particular terrestrial application we already talked about. Now, when you want to really concretely want to make it into parallel programming, what you want to do is basically to create this domain into 4 different pieces, for example, and each of them is still computed by a process. But you know, basically, as they are very close to each other, this is now this nearest neighbor idea, they still have to exchange lots of physical parameters in order to understand the application as a whole. Hence, here MPI is used to send data to the other processors or to collect it. And the same is actually true for the nest. You know, the human brain obviously is very connected and not isolated from each of its different parts. So when you want to see this a little bit in the kind of domain decomposition, there's still lots of message exchanges necessary in this particular part of this parallel application. And these codes can be quite challenging, quite complex. And this justifies that HPC and the overall idea of using HPC for scientific programming, engineering programming is really basically today a kind of, let's say, expertise area of its own. And we see here mostly the approach, what is done in this kind of sciences or engineering. You have experiments still where we observe nature really with measurements and so on. Then, of course, we have certain theories that we basically have existing, I mean, the law of physics all around it, or we basically create models of aircraft and understand there's turbulence and so on. Drag reduction is something what we want to understand. So lots of questions in theory, and we have data from the experiment, really maybe from a tunnel or a 3D printing small model. But what we really then want to understand, if we go back, how we can create a model of this as a scientific application in HPC. And these are often numerical calculations with simulations over time. And this would be focusing on several different pieces that would use HPC, but would have a very specific focus, like for instance here, understanding the stress of the materials in the turbine, or the turbulence of the aircraft as a whole, or basically the turbines of the one basically turbine. So you see several different pieces. Again, the big problem will be crunched into smaller pieces in order to understand it. And thus it basically connects the experiment that we have with the theory, making it more or less a bridge to this, right? Instead of being in competition with these elements, we still need experiments, we still need the theory. The HPC models that we do based on, numerical methods using known physical laws is still very important. And many of these leverage then, because these are very complex applications and very complex computations really, these then basically over a specific time that you see here, the rotor of this particular turbine is basically the time. And in this, basically, we will exchange messages for this model. So much for the introduction. And we will see then when basically we have the second part of the course with the physics, then with CFD, this becomes much more clearer, more and more. And until then, we have also reviewed MPI a bit more to understand then what this message passing is. So let's look a little bit on data science applications, but the same way. Really, you see here, clustering algorithms are already identified with you before. And when you have now the scale of thinking, this is a small city of Bremen, where you want to, from laser scans, a point cloud, recreate the city. Basically, you see here a little bit where this laser car was driving and then shooting around it, and then basically got a point cloud, which we clustered back to the city of Bremen. You can do this on a country scale as well. And then suddenly the data sets and the point clouds get very interesting and very high amounts of data, so big data. And for this, parallel computing will be essential. And we will talk in a later lecture also about this. But you see here also processor 1, processor 2, you would do similar things. You crunch the big elements into different pieces. You make sure it's not basically more or less equally amounts of points that you use then for clustering. And this HPDB scan that I was alluding to earlier here from one of my PhDs in the past is really a beautiful code that scans quite well, using here MPI, for instance, in the red. But you see also already alluding to the use of MPI and OpenMPI at the same time. So distributed memory and shared memory, you get even better performance on different data sets. And we will review this later just to motivate you already. Not only everything is based on physics, also today, data science applications are really leveraging MPI and these parallel computing concepts as well. For this, the MPI usage in cluster modules, for instance, is quite important. We have high single thread performance, so really a good number cruncher if you want. And then the interconnect will be very important. As you remember, we talked about that HPC really makes an emphasis on this interconnects. Let it be InfiniBand, where you can then really with MPI quickly do message exchanges between all of these nodes in order to solve a computational problem very fast. And these computational problems could be from high energy physics, earth science, space weather, different ideas. And of course, in this course, we basically focus a little bit on computational fluid dynamics, but of course, many others do that as well, which is also reflected here, of course, in the idea why we still in the modular supercomputing architecture also need this particular part, the cluster module, which is basically beautiful for MPI applications. Now, thinking a bit more towards how I can actually think more in parallel. So the network communication is, of course, more or less hidden, which is nice. When you think about MPI, you, so to speak, have a nice functional setup, which enables you with parallelization, send and receive messages. We will see that in a moment. And of course, then it needs to be well integrated in the domain code, which is more the challenge. So you would have a particular time, you have this race car with different elements on stress of materials you want to understand, maybe also the airflow to optimize designs of the F1, or you basically have a complete different application where you want to maybe understand the heat in the room. So you have an initial heat map, and then basically after 50 rounds and using physics, you want to understand how much is the heat in the room, for example. Also, always, of course, taking into account your neighbor status. So hence you come to also lots of these message exchanges in this cluster, leveraging then, of course, the idea of the network. But to really then create this application, we will look in this in lecture 3 again more, you would have a good parallelization methods or a good parallel idea, maybe do again the Cartesian in the room in 3D, then writing manually good MPI code is already let's say something which today here and there you maybe just reuse libraries, but still in a way you apply the MPI parallelization, and with this you kind of still to the idea that this should be high performance, and you can do many things wrong there that we will also review. But the key challenge then is in the end that this all code, the whole idea of the application should integrate very well in the problem domain code, right? The computational fluid dynamics to make it really faster, so to really understand the problem of the kind of technical domain we want to tackle, like the CFD applications you have here, for instance, with the airflow around essentially the race car. So hence, to program this is one thing, but to integrate it then with all the physical formulas into the real application is another. So while MPI gives you a very nice idea of how to send and receive data sets, even your own ideas of data units that you can create with derived MPI data types and so forth, the idea is still to think about how I can apply this to all these different applications. And with this, it's actually getting much more complicated than just what is shown here on the top with all this send and receive simple messages. So we will see this, how this evolves also in lecture 3 when we have the domain decomposition at the same time, where we then also leverage the idea of MPI programming. Now, a little bit more about MPI before we dive more and more to the details. It's really a so-called de facto standards from the MPI forum. In a way, you would really call it in HPC a real standard, which is existing on almost every HPC system today. And actually, the interesting thing is, as I was alluding to, it's not only C in MPI. There's also actually today also MPI for Python. There's Fortran implementation, C++ implementations. One of them that we already know is the OpenMPI implementation, which we can use and we'll also use in our assignment on Newton. And the idea is, of course, that this standard gives you 200, 300 routines, has quite an old history you see from 2 up to 4 and more versions new. But of course, normally you would use up to 20 more regularly. So from this 200 or 300 even maybe functions, you would have a set of core set, which are the collective send receives and a couple of others to create communicators and so forth, which are very popular and very often used. But then if you tune your messages with different ways how you can implement then parallelism, you can also, of course, reuse then parts of the standard which are broader. The way how it works in a way more illustrated a little bit abstractly is that you have a memory space that we discussed already. Let's say you have a variable A that is existing in this process 1 in the memory space as data. And just this you want to actually send to someone. So you need to identify this someone. Let's say this 2 is a process 2 and he should get an A. Now, the point is, because we are in parallel, this processor 2 should also be prepared to receive. Think it like a ball, and you play ball with someone, and you think you're actually playing ball, but the other one is looking somewhere else, and you basically pass a ball and it directly rams into the face. In other words, this person was not ready to receive the ball, right? In the same way, we see here the send and the receive operations of the MPI standard is a very trivial example. Prepares the process 2 to be ready to receive. It has its own idea of what A is, because these are different memory spaces. And what it has to do is basically to make space for another variable where it can receive the 23, which brings us here to the B variable, which is indicated then, which will be filled with this receive operation then from the value I get from the send operation, which is A for processor A or 1, and then basically filling the B of process B at the process 2 here. So it's like really thinking about the ball game being ready to receive also when you pass the ball is an important part of it in the simplest way how you can do it now here. It's really a communication library, which is really relatively easy. So you abstract away many of the IP, TCP, low-level functions, which you maybe know from more HTTP-oriented lectures. You basically abstract away all the security that you have. So in a way, it's unsecure communication, but it doesn't matter because we're still within a big other system, which is protected differently. And then there's also this point-to-point communication that you see often here is basically one of the ideas, but also the idea of using essentially many others, which are the collective function then, where you maybe want to send from one processor to all the others is also one part that we want to have here. And the idea is really to have the standard as a way of applications portability, that you basically can now take an application with MPI and move it to the different HPC systems that are available today. So this enables portability. Another way to look at this is basically you see here that we have different HPC machines. Both want to run this nice parallel application around the F1 Formula 1 car. And we have an MPI library on both. So it's probably relatively straightforward to shift it to this. Of course, it will execute quite nicely, but the performance itself is, of course, something which is not directly portable, right? Meaning that maybe the HPC machine B has a newer generation of CPUs, much better performance. The code will run, which enables us now to talk portability, but the performance might be different, which is, of course, then something which is also motivating the portability, maybe from an older machine, for example, to a newer machine, without much, let's say, technical work to be done. Of course, you have to measure the time again on this new machine. And still, this is something which we can enable with MPI nicely, but of course, it has its limits, that, of course, the execution time is not exactly the same. Mostly the HPC machines will all have the different ways how their architecture looks like. Let's say, again, different ways of what CPUs are there, which clock frequency, and so on. Just to say, again, a few words of warning, it's not really something what you should use over the internet. As I said, it's quite unsecure. It's not really another one of those libraries you can use for that. It's really the idea rather to simplify parallel programming within a HPC machine. So not crossing any nodes, not crossing anything. And this is basically something which is a very, let's say, low-level plain way how to program parallel programming and not really having security into account. So don't use it for chat clients over the web services in the internet. That's really more a kind of low-level network library within a cluster. Now rethinking the idea we set here, putting that more abstractly to understand the message. Again, you would have a compute node with its own memory space, as we said, and we send it over, which is now the send operation. And basically this processor, the other one, needs to be really ready for it. So that means we have to have a receive operation. While it only has its own data already there, it needs to be ready to receive this new data set coming basically from the other processor. And that is what we call point-to-point communication in MPI. So one processor sends, let's say, some data aspect to another processor, and the other processor really need to be ready to receive. So the simplest way of a, let's say, ping message Then the broadcast, that is starting and looking to a little bit to the collectives. And this is now really something where we maybe go a little bit quicker now through this MPI collectives. I will demonstrate them also in the next practical lecture. And then you have some, let's say, assignments to do, then it will be very clear. Here it's very trivial thinking about that one processor wants to send to all of the other processor one data element. You say it's a one-to-many operation, which helps us, of course, within a specific communicator. That is something we will call also later on. And you can think if you have an array of sort, you maybe also want to scatter this. So you also again send from one to many others, but not the same data. So you scatter what you have in the array, for instance, here with the different data items to all the other processors. And they all look very similar in the idea that it's all a one-to-many operation. Now, when you basically now want to collect information, you can do this also and think all the other processors maybe should give me the update of a specific data item. And then you can basically fill your own array from the data that is coming from basically many other processors. That is what we call the many-to-one operation in Gather, for instance, which is very popular. And then we could also make an add-on, so to speak, to this, not only sending the data, but perform, let's say, a very simple operation already with an operator you can define. Here's an example of the plus operation. So not only collecting the data, but while you do so, you already would also put the global sum, for instance, of all these data elements. While each processor maybe is computing this differently for whatever reason, this one processor in the end would have then the result. And this operator can be choose from. It could be basically doing the maximum, sum, etc. product, and is also often used in practice. Now, this is basically more the relatively rough intro to all this different, let's say, point-to-point communication to the collectives. And we will have this again and again in the couple of lectures that are really coming now in the next couple of lectures until lecture 5. Also in lecture 4, we will do this much more advanced when we think about the Cartesian communicator. That is more or less this. In the moment we have an MPI communicator, we call MPI com world, which is a world of all the processors in, which you see here, and each of them will get a so-called rank. So this is very important for us, starting always from 0 up to the number of processors -1. And this is how we identify all these different streams, or basically parallel execution streams or lives, so to speak. And what's possible is with MPI, we can put them in different groups from this MPI com world. And then we have two communicators. We will also see in lecture 4 how we do this. And then in each of these communicators, it will have another rank, basically compared to the MPI com world rank. And this enables us to define, so to speak, the so-called communication aspects, or the idea where you want to communicate. One example is here nicely shown, for instance, on the right side. You would use this communicator that you defined more or less for the wave propagation. So some processors are actually doing this, while some specific processors maybe are much more thinking about the sailing boat going over the ocean here and actually computing this parts of the physics. And this is more or less the introduction. I have here a quite interesting summary video again, which is very similar like the, let's say, illustrations I did. A little bit another viewpoint, and also capture the message that actually you have MPI for Pi these days, also in Python, but still I think a lot C is used, which also we will explore more and more. This is all I wanted to leave on the table for you in the first part of the lecture. I encourage you to check out the video. It really helps the understanding. It's not from me, it's actually from someone else, but it really enables you to capture the material of the course and MPI at large better. So we break here for 10 minutes and then we continue with the second part.